Good morning and welcome to another exciting podcast from the UK District Energy Association. Today I am delighted to be joined by the founder and managing director of Hevasure, Steve Munn. Steve will be talking to us about using real-time water monitoring to prevent corrosion in heat networks. So without further ado, Steve, would you like to kick off by telling us a little bit about your background?
Yes, hi there, Simon. I've always had a passion for innovation and science and engineering. So I really started my education in science really at Bath University, where I did materials science. Subsequent to that, I've got a master's in information systems from Sheffield University. But my early career really was working as a scientist at companies like Lucas and Johnson Matthey, where I was working on things like display systems and electronic components and also sensors. In the 80s, I was working at Mitel Semiconductor in South Wales, which was great for me because it combined my interest in technology with my love of the outdoors. So I was living and working in South Wales, which was fantastic for me. And then later on in life, I then worked in various IT sort of project management roles. And that took me to about 2011. And at that time, I decided to join my brother, Dr. Phil Munn. He'd set up Midland Corrosion in the year 2000, and he was wanting to expand. He was wanting to expand the business. So I thought there was an opportunity to work together. And when I joined him in 2011, we were able to put our heads together and use our knowledge of materials and measurements and that sort of stuff to do a lot of failure investigations.
Right, interesting. Failure investigations on what type of systems would that have been, Steve?
So these were basically, it was interesting because when Phil had set up Midland Corrosion, he actually felt that he'd be getting lots of inquiries from all over different industries and things. But I would say 95% of the inquiries were coming from failures of closed systems, closed heating and chilled water systems, commercial systems. And it was quite obvious there were some really major issues there. So with my knowledge of materials as well as and Phil's knowledge of corrosion as an expert in that, we were getting called into some major failures at the time. There was a typical example where we were going to Northern Ireland quite a lot, and there was a failure of the heating system at the Royal Victoria Hospital in Belfast. And I don't know if you know about this, but it was a real sort of eye-opener for a lot of people in the industry. It delayed the opening of a critical care unit by about a year. The costs run into millions and millions of pounds. The whole system had to be stripped out. And we were acting as expert witnesses at the time. And we were taking water samples, we were cutting out bits of metal and analysing them in the lab, working out what had gone wrong. And then we were also going to site and we were putting sensors in and we were doing measurements. And these were retrospective. So after the damage had occurred, we were trying to work out what had gone wrong.
Was this a fairly old pipe that the damage had occurred on?
No. It was a new system. So it had gone wrong during the commissioning stage. But it really struck me at the time, and I almost remember to the day now discussing with Phil, why are we waiting to get called in to do retrospective analysis on what has gone wrong when can't we come up with an idea to actually monitor these systems before any damage occurs, put real-time monitoring systems in. So Phil said to me, I think we should set up a real-time monitoring system. And at that time, you go back to 2011, 2012, the IoT information, the IoT industry was really in its infancy. So data acquisition systems were very analog based, very clunky. The sensors didn't exist. But at the time, we decided, so at the same time as I'm doing failure investigations, about 50% of my time I dedicated to looking at developing a real-time monitoring system, working on different prototypes and things like that.
Sure. Interesting. So how many years ago would this have been, just to be clear, did you start doing that?
Probably about late 2011, 2012.
Okay.
So a lot of the time I was finding out what was available, what sensors existed, what different data acquisition systems existed, how they worked and stuff like that. So really what happened over the next couple of years, I was developing prototypes, and that eventually came to the situation where we had something we needed to do some field trials. And I remember we did a couple of field trials, one in the UK, and at that time we were very close. We were doing a lot of work with Spirotech in Holland.
Right.
And we went out. Funny, it's a bit ironic actually. Our first field trial was on a district heating scheme.
Okay.
In the Netherlands.
Oh, right, interesting.
It was, and what was quite funny about that, and a bit of a lesson that I learned was the system. Yeah, we learned a lot. One of the things I did learn was don't do field trials in foreign countries, because if something goes wrong, you have to then jump on a plane, fly out there. I remember going out there. There was a fault. It wasn't working right. I went out there, took a couple of days out of the office, flew to Holland, and it was just a wire that had come loose. It took me 5 minutes to fix. So yeah, we learned a lot. It gave us the basis for developing what will become our first product in 2014. But yeah, it was a bit ironic. Don't do field trials in foreign countries.
Yeah, absolutely. So we've covered what sort of made you decide to develop a real-time monitoring system. Can you tell me a bit more about Hevasure Limited? What's your focus, where you're based, and what you're up to now?
Yeah, we absolutely focus on real-time monitoring technology for closed systems, heat networks and closed commercial systems. So we don't get involved in domestic. We're purely commercial, heat networks, closed systems, heating and chill water systems. So we are, if you like, the developers of the technology. We are the OEM. We manufacture the system. So we work with a lot of local suppliers around the area where we're based, which is in Derbyshire. So the manufacturing of various components to our own designs. Our motherboards are made in Sheffield. Our manifolds are made in Buxton, and we get some components made in Leicestershire. So we try and work locally with suppliers. Like I say, we're based in the Peak District actually in Derbyshire. So it's a lovely part of the world. So looking out of our office window, we see sheep and cows and things, which is quite nice. So Hevasure really focuses on developing the technology, and that's ongoing. We supply the product, we assemble and test the product, and we provide the associated services. So it's not just a physical bit of hardware that we manufacture. There's obviously all the data analytics. I mean, everything at the end of the day is about the data. It's about getting the data out of these systems and being able to have a data analytics platform that enables you to present the data and to help identify any causes, what's causing the systems to fail or whatever. We tend to sell through resellers, value-added resellers. We don't tend to sell direct. Then it's a deliberate decision, because I could have grown Hevasure to be a large company with 50 people or whatever, but we decided some time ago to focus on our strengths, which is developing the technology and building the product, and then to use other companies who can sell and support our systems in service. Okay.
Could you tell me a little bit more about what you'd expect as a client, somebody who buys a Hevasure solution, what you'd expect to see on site? How does it interact with the system? How does it actually connect into the pipework? Is it a large unit, a small unit? Sort of just give people a bit of an understanding of what they would expect if they had one of your systems.
one of the things I really set out to do from the beginning, and I learned when I was trying to develop the system, is that they can be really complicated to set up, all the different configurations and wiring and everything like that. So what I wanted to do was to provide a product which was as near to plug and play as possible, so that all the sort of connectivity, all the interoperability of the components, all the firmware and software was fully integrated and fully tested. So when it leaves here, we test the product, but make sure obviously it's robust and it doesn't leak and things like that. But what we also do is we ask our clients to fill out a pro forma, which will tell us a little bit about the system in terms of what chemicals they're using, what the makeup of the water is, what pressures, what temperature ranges, and things like that.
Okay.
So we can configure the unit before it leaves site. So all the different alarm levels, if you like, all the different algorithms we build into it are already built in. So, for instance, one of the algorithms we build in is, if you were to tell me that you're based in London, it's a hard water area, and using a molybdate-based inhibitor, whatever, we have got a database which will tell us what is the expected conductivity for that system.
Okay.
We then build in an algorithm into our system that will convert the microsiemens conductivity into a dosing level.
Okay.
Because if you like, microsiemens doesn't mean a lot to a lot of people in the plant room.
No.
But if you said your dosing is spot on, or you're 10% underdosed or 20% overdosed, that's a lot easier for people to deal with.
Okay, so it's giving you a bit of a feedback loop as to what you should be doing in terms of actions you should take.
We're trying to make the job as easy as possible for the end client. We appreciate these are busy people, they've got lots of different plates to spin. We want to give them something that is, if we can do it as much as we can beforehand to make their job easier, then that's what we do. So the product goes out, we set people up on a remote dashboard. I'm going to talk about this later because there's different models of product. But that really was a driving force. And I know there's systems out there, monitoring technology out there, but it still sometimes requires the client to do a lot of work themselves. I mean, I actually bought a corrosion sensor a few years ago.
Uh-huh.
And I was given a manual, sort of, 50 pages thick or whatever, and I had to buy all these subcomponents. I had to download certain software. I had to do this, and then I had to integrate it all together. And for even someone with a bit of a technical background like myself, it wasn't straightforward. So you can imagine FM teams, they're not necessarily going to be acquainted with IoT technology and data acquisitions and things like that, systems. So we want to make their job. We don't need them to get involved. We do it for them as part of the build.
Okay. So just expanding on what it looks and feels like when you're at site, how does it physically connect into the pipework? Do you need a sort of a half-inch tapping that you connect in to run it? So I think that listeners would be really interested to understand how it physically integrates with the system. Can you tell us a bit about that, Steve?
Okay. So the unit itself comes in an enclosure. It's about 0.6 of a metre high, 60 centimetres high. So it fits on the wall or on a framework. Okay,
so a small wall-mounted cabinet, essentially.
Yes, small wall-mounted cabinet, and it's got a local display on the front of it. The water feeds into the unit through a manifold past all the sensors. So there's an inlet and outlet on the opposite sides, and the units would sit in a bypass loop, so it's sampling the water in the system. So typically we might put it across a dosing pot or something like that, or if it's sat in the return pipe work, we'd have a little shunt pump just to make sure water's coming through. But sometimes it's easier to put it in a situation where you've got a pressure differential between the inlet and the outlet, so you just connect it through, and you basically, it's not sensitive to flow rates. We just need to sample the water coming through the system.
I know that sort of pressures and temperatures. Is there a limit on the pressure and the temperature that the system could operate at, where your system can work with, or is it fairly pressure and temperature tolerant?
Well, basically, if you look at our technical spec and UKDEA compliant as well, we specify it up to 82 centigrade and 10 bar pressure. So we actually test it before it goes out to make sure it's actually fine. But we've tested it to far higher than that. We've tested it to 16 bar. All the components are designed to take high pressures. But we give it that margin of safety, and so we say 10 bar and 82 centigrade. The other aspect about installing the system, we need to know how that data is going to get out from that plant room. So we've got various ways to do this. We've got if it's a cloud-based model, then we need to get the data out, and that either goes via the mobile phone, the GSM network, so it's got an inbuilt SIM card, or it works on Wi-Fi, or it can connect through to the building LAN and get the data out that way. We also have a BikeNet model, which connects through to allows us to connect the data through to the BMS. So it will send the live data plus any alarming through to the BMS as well. So that's important consideration. One of the other aspects of our system, which is really important, we'll talk about the different sensors and parameters we measure shortly. But a really good input into our system, we can measure water flow through the makeup line. So a good indication, if you've got a leak, or you're trying to explain why oxygen's got in that system, it's good to know whether or not that system has been airtight, it's been watertight, or if you can detect, say, for instance, you've taken in 50 litres of fresh aerated water, that explains why oxygen's got in it, it explains why your inhibitors got diluted, etc. So it makes sense to position the Hevasure unit within 10, 15, 20 metres of the water makeup line, so you can take a feed off the water meter just to check whether that system is remaining closed or whether you're taking in fresh water into that system.
Okay, cool, excellent stuff. So moving on to other points, sort of what attributes do you think people should look for when choosing a water monitoring system, Steve?
You need a range of sensors. So the idea of on what we see, and we don't forget we've monitored over 200 systems now. You very rarely get just one parameter changing on its own. You will get a lot of parameters changing, and that helps to identify the root cause. So what you need to try and do is to have a system that tells you that things are changing, or in fact tells you it's a healthy system as well. And I'll talk a bit more about that. But if things do change, you want to be able to identify the root cause and to put in a corrective action. So typically, I'll give you an example. Dissolved oxygen is the primary driver of corrosion in these systems. So for dissolved oxygen, you can measure that, and we can put an alarm on that once if dissolved oxygen goes up. We need to know why it's gone up, and dissolved oxygen doesn't normally change on its own. It's normally because you've lost some pressure in the system. So we measure the pressure. So that's one way the oxygen gets in. So in a tall building, you need 1 bar of pressure for every 10 metres. So if you've got a building that's, say, 30 metres high, you need at least 4 bar down in the plant room. And you've got static pressure and dynamic pressure taken into account. So we measure the pressure. So if we see dissolved oxygen go up and pressure dropping, we know the cause is associated with with the pressurization issue. Equally, like I was saying a few minutes ago, another way that oxygen gets in the system is because you've had a leak or something, and you're taking in fresh aerated water into that system. So it's good to measure that. In terms of what we do, we want to measure the factors that influence corrosion. We then, so dissolved oxygen being the main one, we want to measure the parameters that cause those to change, and I've explained about measuring pressure and makeup water flows and things like that. We also want to measure corrosion itself. So we look at corrosion of different metals. So here we show that we have a number of different sort of corrosion sensors. And one we have a steel anode with part of our galvanic current sensor. And if that steel anode starts to corrode, we pick it up in terms of a milliamp output. So if there's no corrosion, there's no milliamp output. If the milliamp output goes to half a milliamp or 1 milliamp, we know that corrosion's taking place, and we've done lots of tests in our lab where we've looked at the output in terms of milliamps, and we've related it to actual metal loss on coupons. So we don't need to put metal coupons into a system anymore. We can say, well, so many milliamp hours is equivalent to a certain amount of metal loss on steel, yeah. So we also have developed a sensor that looks at the corrosion within crevices. So if you look at crevice corrosion, it's the early onset of corrosion normally happens within crimp joints, weld seams and things like that, where you get this local environment, local corrosion cell setup. And you can't buy a crevice corrosion sensor, they don't exist. Well, they do now because Hevasure developed one. We developed and patented one. So we look at corrosion within crevices.
Correlates to the corrosion of the coupons. Yeah, absolutely. Interesting.
No, it doesn't. It's not a sophisticated device, but it does tell us whether or not it detects whether or not you've got crevice corrosion. And so what we have to do is combining all these parameters together, so you get the real-time measurements. But it's how the data analytics behind it, how you present that information in a user-readable form, in a form that people can interact with. So we have it's important, I think, where it's allowed for data security reasons to get that data out remotely, up to the cloud, get it displayed on dashboard and mobile devices. And the real-time data is best presented in a sort of rag stated red, amber, green. So red is obviously way out of tolerance, and you need to take action. It's a call to arms. Something needs to happen. If it's amber, it's going to be out of tolerance, and if it's green, it's where it should be. So in the ideal way, you look at the dashboard, everything's green. It's all hunky dory, and you can sleep well at night because everything's where it should be. When things start to go out of tolerance, you need automatic alarming. But it's not just about the instant values, it's about how things change over time. A healthy system has very low dissolved oxygen, but all the other parameters should be nice and level. They should not be changing. They shouldn't be fluctuating. So when you look at some systems and the pressure's up and down and the conductivity is changing and things, that's not a healthy system. So you obviously need this graphical view over time, what's actually happening. It's also good as well to look at the cumulative effect of things.
Steve, could you tell us a little bit more about the types and numbers of sensors that you have in your system and the sort of the parameters that you measure, please?
Yes. What is worthwhile thinking about is dividing the sensors into different groups of sensors because they do different things. So with our system, we have three different groups of sensors. One group of sensors looks at what I think of as the mechanical integrity of the heating system we're measuring.
Yes.
Another looks at the water itself, look at the condition of the water and changes in that one. And then another group of sensors looks at the corrosion that's happening for the metals in that system.
Right.
So if we look at the mechanical integrity, these are supposed to be well-engineered, airtight systems. Yeah. So in the ideal world, they don't leak, they're completely airtight, and they're completely closed. But the reality isn't like that. And as we know, these systems do get opened for either planned maintenance or because of leaks or whatever. So what I regard as our mechanical integrity group of sensors looks at the oxygen level, dissolved oxygen. It looks at the pressure in that system. So a healthy system should have very low dissolved oxygen. It should have stable pressure at the right amount that holds up the column of water. So in a tall building, it needs higher pressure. It shouldn't be fluctuating up and down, and it certainly shouldn't be fluctuating with temperature. If pressure goes up and temperature goes up, it means the expansion vessel is not set up correctly. We need to make sure that we're not taking in excessive amounts of makeup water. So we've got an input in for the water makeup into the system. And then finally, okay, it's not mechanical integrity, but we measure temperature as well. So is the temperature in the range? And if it's a cooling system, a chilled water system, for instance, we obviously need to make sure that's been applied properly. And if it's a heating system, we need to make sure it's in the range as expected. So that's our mechanical integrity group of sensors. For the water itself, we measure conductivity of the water. Two reasons really. If it's one that's got chemicals added, inhibitors, we need to make sure that the level they need to be, the dosing's at the correct level, and again, it's not fluctuating. So if conductivity changes in an inhibitor system, it's normally because it's getting diluted, or because it might be because of some microbial effect. So nitrate-based inhibitors, if you get nitrate-consuming bacteria, that will change that. And also, pH is a good indication of the stability of the water in the system. So by measuring these, we can tell we've got case studies where we've had cross-contamination. All of a sudden, the conductivity and the pH just changes rapidly. Often these might change gradually, or in the case of a leak, the conductivity would change. And like I said earlier, it's very rare that one parameter changes on its own. So if suddenly the conductivity suddenly decreases dramatically overnight, that's probably because you're taking in a lot of water into the system. And then the final group of sensors, we look at the corrosion in the system. And we can measure the corrosion rate. We should measure the corrosion rate of the metals, particularly steel. But what we can also do is, don't forget, if corrosion is high for a short length of time, it's not really an issue. You do get corrosion, for instance, when you first fill up a system or during commissioning. It's if that corrosion happens over a long period. So if you've got a corrosion rate of 0.001 millimetre per day, per whatever, that's not an issue if it's a short time, but over the course of several months or whatever, it's the cumulative effect over time. So if you can, and that's what we do with our Hevasure system, we've got an ability to measure the cumulative value of this. And the other sensor, of course, is the crevice corrosion sensor, which I mentioned earlier. So the crevice corrosion sensor is a detector that detects the early onset of corrosion within what typically occurs in these systems, weld seams, crimp joints and things like that. So those are the group of sensors we have. Sometimes people are asking about microbial sensors. Can you measure microbes? Well, you can't really, not in real time, because all the work done on that one, it takes time to develop that microbe in a petri dish in a lab for measurement. It's not an instantaneous measure you can get. But what we do in that respect, and the experience I had at Midland Corrosion Services, is if these systems, and don't forget when they're engineered, the surfaces are clean, they're well-engineered systems, if they're kept like that, microbes don't really get the chance to adhere to surfaces. So microbes are only an issue if you've got dirty systems in the first place where they can hide under corrosion tubicles or within parts that are under biofilms or something. You keep that system healthy and clean, then the microbial issue really doesn't really happen.
Cool, interesting. So that's really about the parameters that need to be measured. We covered earlier a little bit about data analytics and how it should be presented. You talked about the red, amber, green approach. Have you sort of covered everything you'd like to talk about in terms of how you're presenting the data?
No, well, not really. The world is changing rapidly in data analytics. With our current model, we've got what we call intelligent messaging built into it. So we have an algorithm built in that if one parameter changes and another parameter, say one parameter goes up and one parameter goes down and another parameter stays the same, it means this. We give a message. So, for instance, I'll give you an example, if dissolved oxygen goes up and it coincides with the pressure drop, we can give a message saying need to attend to the pressurization unit or whatever, because it's allowing oxygen ingress into the system, or equally if conductivity changes or pH changes. We've got messages behind that, which does a lot of the interpretation to help identify the root cause. And at the end of the day, it's no good identifying there's an issue unless we can identify what the cause is and help people to be able to fix it. So we've got that already. What is really exciting, we've not really announced it, but we've been working with Cranfield University on machine learning and artificial intelligence. So Hevasure has got 12 years now worth of data on 200 systems. We've got an absolute wealth of data, so we know obviously what is healthy, what isn't healthy. We can look at trends and stuff like that. So we are shortly going to be announcing to the industry about our move towards a much more intelligent way of looking at data over time and presenting the information to the users. So basically either reassuring people that they've got a healthy system with no issues, or this system is vulnerable to corrosion because it's got these things happening. So this automatic analytics that we're building into it will not be just looking at instantaneous values, it will be looking at the history of the previous few weeks and things like that, and to see what is changing. So it's a very exciting time in data analytics. I mean, artificial intelligence is sometimes overhyped, and what we are looking at is it's not so much artificial intelligence, and people don't understand the difference between machine learning, artificial intelligence and data analytics. A lot of what is behind it is statistics. You are looking at a wealth of data, thousands and millions of data points over many months, over many years. That tells a story. Whether it's significant or not is another issue. So it's quite surprising. Working with Cranfield University, we've been able to determine the correct statistical approach to looking at this wealth of data to put real meaning on what's happening. So this is an exciting time for us, and we want to be saying more about this in the coming few weeks and months.
Okay, well, we look forward to that. Moving on, is there some case studies you'd like to discuss, sort of things that you found in the field that you'd like to tell us about?
Yeah, these various scenarios. I mean, we go back right to one of the first clients we ever had was the Francis Crick Institute in London. And for those who don't know the Francis Crick Institute, it's right next to St Pancras Station behind the British Library. I believe I'm correct, it has 1,600 scientists working on diseases, cancers and these cures. So it's really mission critical. It's not just the heating and cooling of the system, it's all the water-based systems that keep equipment cool and things like that. We've been monitoring there we started 10 years ago, and we've put more systems in there since. What the head of estate says to me the whole time is, do you know what, we've got healthy systems, we don't really seem to have any issues, but what the Hevasure system tells us, it confirms it is healthy, it confirms we have got no real problems with our systems. He said, you don't know what that's worth to us. We've got a building here which is costing an absolute fortune to run, and to that level of reassurance means I can sleep at night. I know we don't have issues.
Sure. So effectively, the client is telling you that your system is giving them a positive feedback, which is allowing them to carry on with their day job and not worry about the water treatment.
Absolutely. So that is a case where, healthy systems, but there's real value in telling people they've got a healthy system. If you think of you as a person and you went to the doctors, it's nice to get that reassurance that you're healthy, that your blood pressure's all right, that your thyroxine levels where it should be, and things like that. So giving that reassurance can be useful. The converse of that is where things do go wrong, and I've got several examples where we've been able to nip things in the bud. One of them goes back several years ago now at Tees Valley Hospital. So Tees Valley Hospital, this was during the commissioning stage. And as you know, when you first commission a system and you do the initial fill, the oxygen levels are quite high, and they should be depleted over the next few days as the oxygen gets consumed during the flash sort of adjusting during that initial few days in the system. And that is normal behaviour. What we found there was dissolved oxygen was not going down, it was really high. This was, I remember it was over the Christmas period, and I'm driving down the M1 taking phone calls from these guys and saying, look, if dissolved oxygen doesn't come down soon, you're going to have to rip that system out and you're going to have to start all over again, because that oxygen has been really high for several weeks now. And I said, I don't know I can't see what's causing it. We didn't have the sophisticated system we've got now, but I don't know what's causing it. But put a vacuum degasser on that system ASAP, get that oxygen out. And that's what they did, and they managed, and they saved that system, and then we got it stabilised and under control. There was a case where, I won't say the name of the company, but we were monitoring the the UK headquarters of a media company, of a social media company in the UK, and we noticed that at a certain time of the day, I forget what it was, 6 o'clock in the morning or something, there was a spike in dissolved oxygen, and there was a change in some of the parameters. It happened every 24 hours at exactly the same time. So we were able to say, well, will you look at your BMS and tell us what is happening at 6 o'clock in the morning that this could happen. And they were able to identify some sort of valve that was opening or whatever, and they were able to rectify that issue and to stop this cyclical event that happening. These things would not be picked up by, the point I'm making, these would not be picked up by water sampling. You couldn't go to a site every 2 or 3 months and pick up these things. You miss all these events. So real-time monitoring allows you to do that one.
Okay, interesting. Moving on, I mean, I've heard about your Aquila 2 range of products. Could you just, we're sort of bringing things to a close, could you just tell us a little bit more about those?
Yeah, so the Aquila 2 was launched in 2022. That's our 4th generation product. And at the time, we'd been working with various suppliers. We took a lot of the systems in-house with our own motherboard designed and built. We took on all the back-end cloud-based services we took in-house and employed an expert in this field. So we took a lot of that stuff in-house at that time, redesigned the system, and we decided to come out with 3 different variants. So our Aquila 2C, if you think C stands for cloud, is our product which allows the data to get out to the cloud, stores in the Amazon cloud, and then we can have a remote dashboard. So remotely we can see what's going on, and the alarms can be set up remotely and send alarms to various people. So that's our 2C model. We've worked a lot now with companies, organisations that are a bit more very data secure. They don't want data going out to the cloud, any possibility of any two-way communication. So we work with government. If you go down Whitehall, there's a lot of Hevasure systems down there. We work with data centres as well, and they are very much data security conscious. So we don't allow any communication external. We have a 2S model, so we think of S for secure. So the data has to go somewhere, so we send that data through to their building management system. So that allows all the everything I spoke about, intelligent messaging, alarming, real-time data, etc., to be sent to the building management system. And then we've got a 3rd variant, which is our 2+ model, which some organisation, this is really popular, the 2+. It's where they don't have that security constraint that data centres might do or the government might do, but they still want the data to go to the building management system. But at the same time, if you just send it to the building management system, it means you don't have this remote diagnostics. It means that Hevasure as a second line support company that provides all the help and advice, and our partners that provide the first line support and advice, we don't get to see the data. So if we can do both, send it to the BMS and get it to the cloud, it means that they've got the benefit of the BMS data there, all stored there, all fully integrated with everything else going on with the building management system. It means that we can offer remote support because we can look down at the data and say, yes, we can see what's going on, and this is what you should be doing now. So that's our 2+ model. So yeah, these 3 variants of the product.
Brilliant. Okay. Well, that's really very interesting. It's been really exciting to talk to you this morning, Steve, about using real-time water monitoring to prevent corrosion in heat networks and find out a lot more about this topic. So a big thanks to Steve for joining me in the UKDEA podcast studio, and thank you to all the listeners for tuning in. And we look forward to talking to you again on another subject in the future. Thank you very much indeed. Goodbye.